will get started with simulators today. So in the previous couple of classes we had some basics of Verilog HDL, and we must now understand that how is the simulator going to take a Verilog code and simulate it internally. Now most of the simulation that is done today, the voluminous simulation that is done today, is at the level of the register transfer level code. So what we are going to learn is how that simulation works, and this actually accounts for the major part of the verification time. So most of the verification time is spent by the verification engineer in writing out simulation test cases and then running the simulator with those test cases and comparing the output of the simulation with the golden outputs. So let's see how the simulator works. So the agenda for this presentation is that we will first look at the compilers for generating the code which is simulated. Then we will talk about the simulators which actually simulate that code. We will talk about the different types of simulators or the taxonomy of simulators and the types of operations that the simulator does. And this chapter is mostly covered from the book called Hardware Design Verification by Lamb. So if you look at the major components of a simulator, there are broadly two parts. One is the compiler, which is on the top here, and the remaining part is the actual simulator. So what does the compiler do? It has again two parts. One is the front end, which consists of a parser and an elaborator, and then it has a back end which does analysis, code optimization and code generation. Right? What the compiler does is it produces some form of code. That code could be a high level language code like C, C++. It could be abstract language code which is interpreted by the simulator, or it could be pure machine code directly generated by the compiler. Now that is actually the compilation of the circuit structure into a simulatable form, and the simulation engine is the one which actually schedules the different events and then simulates each of those blocks one by one. And simulation control is something which the user can control to control various aspects of the simulation at runtime. Alright, so every simulator typically will consist of a compiler, and then there is the simulation engine which actually performs the simulation using the code which is generated by the compiler, right, and a few inputs that are received from the simulation control either by the simulation control itself or directed by some user controls. So let us go into the details of each of these. So first we start with the parser and the elaborator. The front end portion of a compiler, which consists of the parser and elaborator, it processes the input circuit and builds an internal representation of the circuit. So if you look at one of these elaborators, what they are going to do is they are going to take the Verilog code and then produce an intermediate data structure. Okay, that data structure can represent the control flow graph of the behavioral models. It can also have a structural representation of the structural parts of the circuit, right? And again, let us see what are the two parts of this and what are their roles. So one part is the parser. The parser interprets the input according to the language's grammar. So as the name suggests, it is the one which checks the grammar, and it creates corresponding internal components or data structures, which I just now mentioned. The elaborator does something more than that. What it does is it substitutes the module instantiations with their definitions. So remember that in our Verilog language, you can define a module once and then use instances of that module in various parts of your circuit. Now what the elaborator does here is that it substitutes these module instantiations with the actual objects that or the definition of those modules. Okay. So the end result of the elaborator is that it is a complete description of the input circuit. Okay. And all the syntactical errors have already been taken care of by the parser. Right. Now what is there in the backend? The backend functionality depends on the type of the simulator. So there are broadly two types of simulators. One is called the compiled code simulator, the other is called the interpreted simulator. Now these are two ends of the spectrum, and in between there are lot of hybrids between these. Okay, and we shall see that there are intelligent ways of using both of these techniques to get more powerful simulators. And within the compiled code simulator again, okay, so these two are very similar to what we see in programming languages also. You can have compilers that compile your program right down into the machine language, or you can have compilers which generate a portable intermediate code which you can take to various other machines, and if that machine has an interpreter for that code, then you can run it on that. Right. So within the compiled code simulators, we have three types of simulators. One is called the high level code. So as the name suggests, here the compiler produces as output a high level code like C, C++. The second one is the native code, which means that the compiler will produce an executable machine language code corresponding to that particular processor on which the simulator is running. And the third is emulation code. Now this is, you had a question? Okay, the emulation code is actually something which gets ported into an FPGA or a hardware platform, and the simulation actually runs in hardware. So there are various other terminologies that people use. One is, the popular one is that it is called hardware accelerated simulation. That's because that typically if you have a complicated environment of the design under test, then migrating the whole environment into the FPGA board is very difficult. So you might choose to have some of the layers of the test bench migrated into the hardware, and the top level choices like which transaction am I going to run, is it a burst read or a burst write, or what kind of data is going to be fed in. So few high level decisions can be controlled from the software. So that's why it's not pure hardware emulation, neither is it pure software simulation. So it's called hardware accelerated simulation. So when I talk about emulation code, this is the code that is going to run either totally in hardware or partially in hardware. And the interpreted simulator works on the principle that the input circuit is compiled into an intermediate language, and we can think of the simulator as a virtual machine which can interpret that language and simulate the code. So this is a typical flow of an interpreted simulation. So just like a processor, this is a virtual machine which can interpret the language in which the interpreted code is generated, and it fetches one instruction at a time of that interpreted code, decodes, executes, writes into the registers or memory. It can handle exceptions or interrupts, and that is the main way by which it actually interacts with the user through exceptions or interrupts. Okay. So it's like this. Now, are you familiar with the Prolog programming language? Any of you? Okay. So there are, you are mostly familiar with procedural programming languages, but there are a lot of other types of programming languages like functional programming languages or logic programming languages. Prolog is a logic programming language, and the reason I talk about this is that typically Prolog engines generate an intermediate code which works on a virtual machine called variance abstraction machine, right. So it's very similar to this. So the interpreted code is taken by the variance abstraction machine, and it actually executes that interpreted code, and the result is the backtracking and retracing semantics that Prolog supports. So this is the what we mainly mean by interpreted simulation. So to give you an example, on the left hand side I have the Verilog code of a circuit which is being simulated. So as you can see here that let me choose a pointer. So here I start by initializing the clock uh, to 1 tick B0, okay, and then after every 1 unit of time we toggle the clock. So clock equal to not clock means just clock is toggling, okay, and after 3 time units we finish. So that finish is a special statement which says that this is the end of simulation. And here we have an always at clock which gets triggered at every change of the clock. Remember that there is no passage or negate here, it's just always at clock. Then at every change of clock what we do is we evaluate A to be equal to B and C, and if A is 0 then we assign P to Q after left shifting Q by 3 bits. So this thing here indicates left shift, okay. This pointer is not very well visible, let me change the color, okay. Now let us see what a generated interpreted code would look like. So initially we assign clock 0, so this corresponds to this, alright. Then we invert clock, okay. Now that's because that from here to this #1 actually nothing, there is no event. You see, clock is assigned to 1 tick B0, thereafter for 1 unit of time there is no other activity. After that the clock changes, right. So that's this thing, that invert clock, right. What happens when this clock is inverted? That triggers this one and results in the evaluation of this, okay. So that evaluation is captured under this evaluate B1, okay. So this whole thing is this. Now let's see what is there in the B1 part. This is the interpreted code for B1, okay. What do? We compute the AND of B and C and assign that as A, and if A is 0 then we left shift Q by 3 and then put the result in P, okay. So this is just a representative intermediate code. So somebody has designed a language in which these functions have that meaning, right. And then after that we again invert clock, this corresponds to this one, right. And then again this change is going to trigger this one, so we call evaluate B1 again, and then finally it reaches here which calls finish, so we have exit, okay. Now note a few things here, that what has the interpreted code done? It has actually somehow statically converted this interaction and produced a linear code, right. So all the events that took place here, like the change of the clock and the corresponding actions, have been inlined here. This in general is an extremely non-trivial task. If you have many modules each triggering each other and many of those are data dependent, then doing this kind of integration is a very difficult thing. So there has been attempts to do this, and the technique is called static simulation, okay, where you don't have the inputs at the time of compilation, but you merge all these always blocks, you merge all these events into a single line of code by considering all possible branches that the code might take, or all possible ways in which the code might execute, right. So it so the input is a set of concurrent Verilog blocks and the output is a single monolithic interpreted code. Hmm. But it's a very difficult task to do, and typically the code size can become very large because of, you know, handling all these different types of ways in which they can happen. But at runtime, you see, out of all those branches only one is going to get executed because at that time the input is known, right. So though the interpreted simulation can run quite fast because all the code is pre-generated, there is no event handling at runtime, but it can actually, you know, the physical size of the code can be very large. So people don't actually use completely interpreted code simulation unless, you know, the complexity is manageable. We are going to look at other types of code generation, which is typically what is followed. And interpreted code can be generated for different modules, but not integrating everything together. That's very hard to do. See, what is this? Okay, so if you wanted to also model the timing here, then you would add some other functions to say increment time by 1. So if you want to maintain the timeline, so wherever you are having these hash ones, so for example after this assign clock 0, then you may want that let me put increment of time here, right, between this assign and input. So you can have another function which says increment time by 1. All right. Now compare this with the compiled code for the same circuit. So what do we have here? Again, this side is the same. Now let us look at the other side. So on the other side, we have this definition. Now see, this is a C program. Okay. So we first initialize clock, declare clock to be an integer, and then we declare all these A, B, C, P, Q as different integers. Then this initialization of clock is here, clock is 0. Now see what happens here. We know that this is going to go through 3 time units. So we initiate a for loop which says for I equal to 0, I less than 2, I plus plus. In each iteration, what are we going to do? We are going to toggle clock, right. So toggling clock is done by this. So clock is, you check whether clock is 0. If clock is 0, then clock's value becomes 1. Otherwise, if clock was 1, then it will become 0. Then after toggling clock, we have to evaluate this. So this is done here, A equal to B and C, and then you check if A is 0, then this, right, and then this is done another 2 times, right, corresponding to the 2 times that this is changing, right, another 2 times or another 1 time, another 1 time. So after that it simply terminates. Now see, here the major challenge was that to parse this code and come up with this line which says that for I equal to 0, I less than 2, I plus plus. So it knows that this loop is going to execute 2 times, right. So but the difference with the previous one is that this can now be directly compiled on any machine which supports a C compiler and executed. The previous one, this one, can only be run on those machines where there is an interpreter for this interpreted code. Okay, and if there is an interpreted code simulator, then the simulator itself will be the interpreter for that code. Whereas here, after the compilation is done, all you need is a C compiler. But remember, these are 2 extremes. Typically, simulators are not going to use purely one or the other. Okay? So this slide shows you the different simulator types. So here is the input circuit. We can generate intermediate code and have an interpreted simulator, and then we call that the simulator type is interpreted code simulator. The input circuit can be compiled into a C++ code, and then we use a C++ compiler to generate the code for the host machine, and then this is called high level simulator. Why? Because it generates high level code. Then we have from the input circuit you generate host machine code directly. So this will run on the host machine, and this simulator type is called host machine. And the fourth type is that it generates a hardware executable, which is then ported into a hardware emulator like FPGA or anything, and the simulator is in the hardware, and so we call it the hardware simulator type. Okay, these are the four broad families of simulators. So let us get into the compiled simulation system structure. So we have the compiled code here, this whole thing. It has several different parts. The compiled code has the instruction memory and the data memory. In the instruction memory, we stored the circuit structure in terms of the connectivity between the circuit components and the functionality of the components. So this is where you are storing the logic, okay, of the different blocks, and this is the connectivity between the blocks. All right. So this is sort of the data structure in which we are storing the circuit, and then here is the data memory, which is storing the values of the signals and the registers, right, because they are going to change with time. As the simulation progresses, this data memory will continuously get updated, and they will be updated on the basis of simulating these components, right. The simulation engine does the following things. It schedules the different activities within the circuit. So it makes which we are going to study shortly, that how does it schedule the events. It will do the component evaluation. What is the component evaluation? Given the inputs of a logic, find out what are the outputs. Okay, that is logic evaluation, right? And then time advance. And as we know from Verilog, that when all the active events are over, there is nothing else that is being triggered at that time. The simulator will start advancing time, and then pick up those events which are blocked on hash delay, right? So that is time advance. And the simulation control, we will see what this does, is the one which controls this activity and can take user inputs to do that. So for simulator architectures, there are, so now when we are talking about simulator architectures, we are talking about this one, okay. This is the architecture that we are talking about, not this. We are not talking about what kind of code it has generated. We are talking about the architecture of the simulator itself, the simulation engine itself, right. So there are broadly two types. One is called event driven simulation, the other is called cycle based simulation. What does event driven simulation do? It evaluates a component only when there is an event at an input. Okay. So whenever there is a change in the input of a logic, then we will propagate that event, right. Now look at this this thing, that suppose I have a logic which has 50 inputs, right, and only one of those inputs change. So it's not really, it's unlikely that it will affect all the gates of the circuit, right. What event driven simulation will do is it is going to propagate that event through the circuit by only simulating those gates where input events take place, right. It will not simulate those gates for which the simulation was already done previously. and they are not changing, because those outputs are not changing. Why should we simulate them again? But cycle based simulation will simulate the whole thing, but it is not going to simulate it all the time. In an event driven simulation, whenever there is an input event, the simulation will get triggered along that path. In a cycle based simulation, even if there is an input event, it will wait until that cycle is over. So in periodic intervals, which are the cycle boundaries, it will evaluate the whole circuit, right? Now as we shall see that there are advantages and disadvantages of both. In a pure event driven simulation, if you have several different activities taking place within short intervals of time in the same clock cycle, for example, you will have lot of events generated, because each of them will start building their own events. So a gate can be simulated many number of times, because their inputs changed, but they did not change at the same time, few microsecond this way, that way. So you end up generating a lot of simulation events. But if you are interested only in the steady state value, because that is the value which is going to get latched into your flip flops at the end of the clock cycle, then we might as well wait for all the inputs to stabilize and then just simulate the whole circuit with that new set of inputs, right? That way the number of simulation cycles can be, number of gates that you simulate or the number of times that you simulate a gate can go down, alright. But the problem is, there we are simulating the whole circuit in every cycle, whereas in a particular cycle only a few things might have changed, right? So there is a trade off between these two, and there are a lot of hybrid simulators which will make use of this trade off. So to come back to this slide, and in an event driven simulation, the event ripples through the circuit until it causes no more events, at which time evaluation stops. And in a cycle based simulation, simulation is performed only on cycle boundaries, not whenever an event occurs. The circuit must have clearly defined clocks, otherwise how would you define cycle boundaries, right? So for this we must have that the circuit has clearly defined clocks, and asynchronous circuits and circuits with combinational loops cannot be simulated in pure cycle based simulation. We are going to come back to this and realize why it can't be simulated and what is the problem there, and then we will see there are simple tricks to get around that and still be able to do cycle based simulation. Okay. So we are going to go into event driven simulation now and study that how an event driven simulator works. So the things that we are going to look at is that there is a notion of an event manager. The role of the event manager is to schedule all the events that are taking place within the circuit. Then we will look at the scheduling semantics, the way the language is interpreted in terms of the way the actual events are scheduled by the simulator. Then the update and evaluation events, there are two different things here. One thing is that a signal actually changes, which is an update event, and the evaluation event is you don't know whether it will change or not, so you still have to evaluate that logic. So that is the evaluation event. Then we will see how event propagates through the circuit and how we do time advancement and oscillation detection. Okay. And finally we will summarize this whole thing with the event driven simulation algorithm. So the data structure, or sort of very high level view of the data structure which the event manager must have, is called a timing wheel, right? So what is this timing wheel? It stores corresponding to each time unit a set of events that are going to take place in that time. Okay. So what happens is, when you process one event, let's say when we process this event, that can generate another say 2 events, one which is going to take place 5 time units from here, another which is going to take place 2 time units from here. So if it is going to take place 2 time units from here, then we will add it to some list here, because from the wheel after 2 time units this is where we are, right. So that will, this event can cause some event here, the scheduling of some event here, okay. And the one which is going to be created after 5 time units is similarly going to be placed in that position of the timing wheel, right. And the simulator will always be in the current simulation time, it will complete all the events in the current simulation time and then move on to the next place, right. Now remember that this shows T0, T1, T2 etc. T1 may not always be just T0 plus 1, it could be that this is the next time window, right. It is not necessarily just one time unit after this, okay. Now what is going to be the size of this timing wheel? See, that is an important design choice. Now when a particular event is taking place, we have to find out how far ahead can the next event be generated, right. Now it could be that the next event is being generated after 64 units of time, then you might say that I need at least 64 slots in the timing wheel for that. But then it may so happen that all your events, they are at a granularity of 4 units. So either they happen after 4 units of time or 8 units of time or 16 or 32, but then we don't need 64 units because the granularity of the time is more coarse, right. So this is something with this which the simulator has to smartly choose, that what should be the size of the timing wheel. If you keep a very large timing wheel, you are using up a lot of memory for that. So that is one of the choices. So events are stored in an event manager which sorts them on time. Events occurring at the same time have an arbitrary order of occurrence. So if you look at the events which are currently in T0, all of these, they can be scheduled in any order. Okay. The event queue may be implemented as a circular queue, or alternatively, popularly it is called the timing queue, but as a data structure it is a circular queue, right. So let us take an example of what we mean by an event driven simulation. So let me draw up a circuit. So let us say we have an AND gate here, okay. So this is the circuit, and let us put some, the current values are like this, that we have, suppose at this point of time this is 1, this is at 0, this is also at 0, and let us name these gates. So let us call this A, B is a NOR gate, C is an XOR gate, and D is an AND gate, and let us name these nets as A, B, C, D. Now let us see that at a given point of time, let us say that this was 1, okay, this was 1. So when this was 1, at that time what were the values that were there? So what was this value? Let me write them out in red. These are the previous values, okay, before any event has taken place. This was 1. What is this one? because this is 1, this is 0, so this is 1, so after the not it is 0. Then what is this one for XOR? 1. And what is this one? 1. Now let us say that we have a fall transition here. Okay, so let us call this event as E1. So what is the event E1? It is a fall transition here. So this input goes from 1 to 0. Okay, so now it is 0. Now let's see what the simulator does. So simulator first reads that this is the event that has taken place. Now it says that it feeds this gate, so it generates an event. What event does it generate? So if this has taken place at time t, so it generates at time t plus 1, because let us assume that each gate has a delay of 1. So at t plus 1 it generates a fall event, right. So a fall event, let us call that E2, and this takes place at t plus 1. Right. Does this event generate any other event? No. So simulation finds that all events at t has been done, so time advances to t plus 1. Okay. At t plus 1 it takes this event E2 and then finds that this net where the event has taken place is at the input of two gates, namely B and C. So what events will it generate? So is there any event corresponding to this? Let's see. Yes. What event takes place here? A rise event. Okay. So let us call this rise event E3. What is the time at which this is going to take place? T plus 2. Is there any other event that is going to take place? Here, right? See, let us look at this. What was the value of this? This was 0. This one is has become 0. So it is going to change. So we are going to have a fall event. Let us call it E4. What is the time at which this is going to take place? T plus 2, right? Anything else to be done at T plus 1? No. So we are done with T plus 1, right? Now what do we do at T plus 2? Get C and get D. Okay. Now see, this event is not driving anything else, but let us look at this gate, this event E3. E3 is in B and B drives C and D. What is going to happen at D? Nothing, no event, right? Because this other input of D is 0. So the output of the NAND gate will remain at 1. So no event, this event E3 is not going to propagate to the net D. What's going to happen here? This is a rise event here, right? At T plus 2, what is the value of this signal? 0, right? Now what is now E3 rises to 1. So what is going to happen? There will be another rise transition here, right? So let us call it E5. At what time is that going to take place? T plus 3, right? So next time advances to T plus 3 and we raise this signal from 0 to 1, namely C is raised from 0 to 1, and then there is no other event, right? So all events have been done and we are at the end of simulation. Now the important thing to note here is that look, that if we just did a steady state analysis, which is what a cycle based simulator would have done, what it is going to do is it will just take the steady state values, namely it is going to take 0 here, 1 here, 0 here and 0 here, evaluate this logic and say that in the end we have C is 1 and D is 1, right. So it is going to evaluate this logic and produce C is 1, D is 1 at the end. But when we did event driven simulation, we are able to see this glitch, that this signal at C momentarily goes down and then comes up. It was 1 at the beginning, it is 1 at the end, but momentarily it went down and came up. The question is whether you want to see that event or not. Now, if you are doing some kind of analysis like power, for example, you want to see how much of transition power is getting consumed. So every transition, every glitch like this is going to eat up some amount of power. So if you want to do that kind of estimation, you will need the event driven simulation, so that you are able to see all the intermediate events. But if you just want the steady state value at the end of it, assuming that this is the change which took place in one clock cycle, you want to find out what are the values of C and D at the end of the clock cycle, then you do not need to do all this propagation of events, right. And the gate C, which was simulated twice, once for propagating E2 and then again for propagating E3, that will be simulated only once in a cycle simulator, right. Is that clear? So this shows the scheduling semantics of Verilog. So in Verilog, events at a simulation time are stratified into 5 layers of events in the following order of processing. The first thing is the set of active events. The processing of all active events is called a simulation cycle. So when we talk about simulation cycle, that has got nothing to do with the clock cycle. Please be careful about that. Clock cycle is the clock boundary, alright. In a cycle based simulation, pure cycle based simulation, our simulation can take place only at the clock boundaries. At every clock change, we do the simulation, right. That is cycle based simulation. For event driven simulation, the simulation cycle is the cycle in which all active events are processed. Then after the active events are processed, then inactive events are taken up. Now in this active event there is a further stratification, because some active events can trigger other events which are blocked on at the rate type of constructs, right. So they in turn will get activated, will create new events, and this is going to continue until at some point of time there are no active events left at all. So that is called the end of the simulation cycle. Then you pick up the delayed events. Now remember that in Verilog you can even have a thing called #0. Now what does #0 mean? #0 means that you process the event which is following this at the same simulation time, but after all the active events. So suppose you want some event to take place after all the other events have finished off, then you can precede that by #0. Now it seems peculiar, why should I use #0? It is not incrementing time, but it is a way by which you can direct the simulator to process that event only after all the active events are finished. Now when after all this has taken place, okay, so this inactive events like #0 something are processed. Now remember we have not yet advanced time, then you pick up the non-blocking assignment update. Now this is the set of non-blocking assignments where it first samples the values of the right side variables, then it updates the left side variables. Okay, so it gets the steady state values of the variables. After the non-blocking assignments have been processed, then the monitors are processed. So these are executed as the last events of the current simulation time to capture steady state values of variables. Now remember that whenever we want, what is monitor? Monitor is where you observe the values for your simulation dump. So when you look at the timing waveforms, those waveforms are the plots of the points at these monitor points. That's where it has sampled the values. Later on, when we talk about assertions, assertions are also properties which are monitored over simulation. They will also be examined at those points. It's just at the end of the simulation cycle, after all the other changes including non-blocking assignments have been processed. And then when this is also done, then we go to the future events. Now future events means that is where you advance time and then go into the future, and then the whole process repeats itself. For each time slot, in reality 4 sub queues are maintained for the 4 groups of events. So there are actually 4 different queues that are maintained for these events. All right. Now look at this example. In this example, we have 2 blocks. This always block at the passage of clock assigns A to X, and this always block at passage clock assigns B to X, and then it does a non-blocking assignment of X to Y and a blocking assignment of C to Y. Now let us see how is the simulator going to schedule these events. Whenever there is a passage clock, at the passage clock it will first make this active, and similarly it will make this one active, and it will make this one active, right. Now the order in which they will be processed is that this and this can be processed in either order. X equal to A or X equal to B can be processed in either order. Okay. After X equal to B is done, Y equal to C will be processed, right. Thereafter, suppose there are no other active events, then we will go to the non-blocking assignment. So there the X will be assigned to Y. Okay. So to conclude this, X equal to A and X equal to B are active events, and their order of execution is arbitrary. They are in the same list of the timing wheel, and they can be ordered in any. The value of Y is either A or B, but never C. Why? Because this statement, this one, is executed after this one. Okay, this is executed after this one, and the value which this one is going to get is either A or B. Clear? This gives you an idea about that the scheduling semantics of the simulator, that it first picks up the active events and then goes into the non-blocking assignment processing. Now the good thing is that you might wonder that why am I learning all this, right? Now the good thing is that if you look at most of the commercially available simulators, for example if you look at Synopsys VCS, there are a lot of hooks which are given at these points of the simulator. So today if you want to build some tool on top of the simulator, you don't have to have the simulator's code with you. There are a lot of APIs or interfaces, functions through which you can get access to the data structure of the simulator or specific parts of the data structure of the simulator. You can study which events are being processed, you can have callbacks set up. So you can say that whenever I am hitting that non-blocking assignment updation, please give me a callback, and you can set a callback, and during simulation whenever it goes to that part of the simulation cycle, it will call your function, and then in your function you can do a lot of things, right? Even traverse some parts of the data structure of the circuit, right? And generate and get whatever information you want. Why is that so nice? Because you can now write your own monitors, your own verification tools which sits on top of the simulator. It gets access to all the signal values at the specific points of the simulation cycle, and you can interpret that, right? So that's a very good thing to have, and I would strongly recommend you to look up a thing called VPI. Okay, just take it down, VPI. Okay, these are some standards that has come up with the standards that are available for Verilog and its simulators, by virtue of which you get access to these routines. All right. So later on, if we have assignments, I can give you assignments based on VPI callbacks. All right. We'll stop here today, and in the next class we'll quickly summarize what we have in this and then go to cycle based simulators. Thank you.